let's just do one example of solving a rational equation. This one's going to be pretty nice. We'll look at maybe a little more complicated examples in class. We don't want to get too complicated. We've got an equation involving rational expressions, and we'd like to solve. We'd like to see if there's any values of x that satisfy this equation. And the key is that fractions are complicated, and if we can express it without fractions, then that's going to be better, okay? And so the key, you just want to remember, multiply by the least common denominator of all the expressions that are appearing on both sides. So let's see what that is, and then we'll see what happens when we multiply it. This one's a little bit contrived because we'll see something very nice. We need to factor that right-hand side, and guess what? That's actually x plus 4, x minus 1. So this isn't random at all. This denominator is quite a bit related to this. Doesn't have to be, but it's going to make things a little prettier. Okay, so the least common denominator is in fact just this right-hand denominator, because x plus 4 is already a factor of that, x minus 1 is already a factor of that. Once again, it's not like we're just multiplying this times this times this. We're finding just the simplest polynomial that all of these things are factors of, and we're in this nice situation that everything's a factor of exactly this right-hand side. Okay, so we're going to multiply both sides by the same thing, which is all we kind of ever do to equations, is multiply or do the same thing to both sides. Here it's going to be multiplication. And let's see what happens when we do that. Let me copy it. The right-hand side is going to be very nice. Oh, whoops, I'm sorry. Okay. The right-hand side, I'm going to multiply by the same thing here, and that's going to cancel out. But let me kind of put it in everywhere. Makes it look briefly rather complicated, but the whole point is that I'm going to be canceling out all these denominators. Over here, I've got a factor of x minus 1 on the bottom, canceling this guy. So let's just go ahead and do that. So that's just going to be a 2 there. Here, the x plus 4s are going to cancel. This whole part of it is going to be a 6. But what didn't cancel was the x plus 4, and what didn't cancel here was the x minus 1. Now, it happens to be, again, because this is a little bit of a simple example, the common denominator we found was exactly the denominator here. All of that cancels down except for the 8. Oh, wow. That is a lot simpler. Now, when you solve these, it's not uncommon. Once you clear the denominators, you might get a quadratic or even something more complicated. But this was chosen to be pretty darn nice. So we're going to get 2x plus 6 is 8x. Plus 8 minus 6 is 2 plus 8, yeah, equals 8. 8x equals 6. X equals 6/8 or 3/4. Okay. Now, somewhat like in absolute value stuff and like root stuff, there is a possibility that we found an extraneous solution, because kind of like roots, division is tricky, and we kind of by multiplying by the common denominator, we kind of pretended that the division never happened, and that's a little bit sketchy. So like a lot of algebraic things, we proceed anyway, but we just know, oh, this is the kind of thing we don't want to be absolutely sure of. The book has a good example in our appendices, has a good example where you do this and you plug it back in and you discover, oh, no, it actually is something that makes the original equation blow up. So you do want to check and be careful. Basically, the only thing that could go wrong is if any of these denominators was equal to 0. X minus 1, so let's see, let's just check that. 3/4 minus 1, not equal to 0. 3/4 plus 4, not equal to 0. And again, this right-hand side denominator was just the product of those two numbers. So I've already checked that when we plug in x equals 3/4, neither of those individual factors are 0. So no denominator is 0, and we're good to go. If we were really careful and we had some time, we would just plug in really, really carefully to check it. But it turns out the only thing that can go wrong here is if the denominator is accidentally 0. And we've checked that, so we're good.